In this QUPES how-to video, we illustrate how to design a frequency selective surface, an FSS, using QUPES. To this end, we consider an SKA band FSS. The FSS needs to reflect in Ka band and be transparent in S band. We start with the TICRA Tools project, where we have defined a periodic unit cell consisting of two layers of square loops separated by free space and an associated frequency object. If you're not familiar with how to set up and analyze a periodic unit cell, check one of our previous videos where we teach you these steps. In terms of frequency bands, we have defined Ka band from 20 to 24 GHz and S band to be between 2 and 2.3 GHz. We have two identical periodic unit cell objects, one for each frequency band. The FSS needs to work for linear TE polarization. As we mentioned before, we consider square loops for the FSS. To define the side length and width of the loops, we have introduced two real variables, L for the side length and W for the width. As initial values, we consider L equal 3 mm and W equal 0.4 mm. We need these variables in order to optimize the FSS. In the Command tab, we have defined two commands that calculate the reflection and transmission response of the FSS in the two frequency bands for normal incidence. We execute the commands and go to the Results tab to look at the results. For S-band, we look at the transmission TE component, and we see that we have low transmission losses in the S-band, less than 0.1 dB. For Ka band, we look at the reflection TE component, and we see that we have reflection losses over 10 dB. We need to improve this by optimizing the FSS geometry. We go to the Optimization tab and create a new Optimization Manager. The two variables that we have defined, L and W, are among the available variables, and we include these into the optimization. We specified relevant bounds for these variables to ensure that the final geometry is feasible. Then we need to create the optimization goals. We click on New Goal, select Goal Periodic Unit Cell, Amplitude, because we want to optimize the amplitude response of the periodic unit cell. Rename the goal to indicate S band, and in the periodic unit cell attribute, we point to the object that was defined for S band. For goal specification, we consider normal incidence theta phi equals 0.0, polarization set to TE, and we want transmission in S band with a target goal of 0 dB. In a similar way, we define a goal for Ka band, with the only difference that we now want reflection instead of transmission. We add both goals to the optimization. We can now define the optimization settings. Let's use the min-max algorithm in TICRA Tools. We create a new optimization setting and use the default values. To add an optimization command automatically to the list of commands, we press Add Get Optimum command. Now we rearrange the command such that we first optimize the FSS and then do the analysis such that we can see the optimized results. During the optimization, it's possible to follow the progress not only of the variables, but also the objective function and goals. We proceed to the Results tab to see the results. For S-band, the transmission losses are still low, around 0.1 dB. And for Ka band, the reflection losses are now reduced to the same, about 0.1 dB. To see the optimized values, we click on the optimization variables. We can see that the width W is changed from 0.4 to 0.2, and the length L is changed from 3 to 3.5. We apply the changes, and we can now see the optimized FSS geometry in the POC tab. This completes the FSS unit cell design, and we can now apply it to a reflector system, as will be seen in part 2 of the video. So thanks for watching this QUPES how-to video on how to design an FSS, and don't forget to watch part 2 for full reflector analysis.